Here's a question. What filament is best for 3D printed gears? This is a robotics platform I've been prototyping, and it uses a spur gear reduction to the wheels in what's known as a portal axle arrangement to give more ground clearance. I want these gears to be strong and durable, but should you print them in PLA, ABS, nylon? I had no idea, so I decided to do some destructive testing, and the results were really interesting. Before we begin, let's be real. 3D printing is pretty incredible, but there is no way a 3D printed gear will ever be as strong or precise as a machined one, or even injection molded plastic one for that matter. So if you need that, I would just go and buy them. But if you have a 3D printer, printing your own gears has a ton of benefits. You can literally download and print the exact size you need with custom tooth count and mounting options, and have them ready for use that very same day, which is a wonder for speeding up the prototyping process. For an example of just how powerful this can be, look no further than Ivan's channel, where he's made countless incredible projects full of 3D printed gears, pulleys, and
spacer!
However, like he's found out many times, 3D printed parts don't always survive real-world abuse. I don't want my platform to chew up its gears instantly, but I also don't want them to deform in such a way that the whole mechanism binds up and potentially burns out my fancy brushless drive motors. So the testing criteria is this. Number 1, determine just how much torque the gears can handle before they start to deform or fail. 2, determine at which torque they do fail. And finally 3, note down the manner in which they fail and if it's repeatable, because in the event of an entire drivetrain binding up, I would actually rather the gear to fail cleanly at a certain torque level and protect the motors, kind of like a mechanical fuse. For testing, I devised a simple rig, 2 gears meshed together with one fixed firmly in place, and I'll apply gradually increasing torque levels until the point of failure. And this is the tool to do it, a torque wrench. Torque wrenches allow you to dial in a level of tightness for bolts, and they're essential for automotive work. To use them, you set the torque level that you want and then lever like a regular wrench until you hear and feel a click, which means you've reached the desired level of tightness. All of the test gears were printed using the same settings out of Prusa Slicer on my modified Tronxy D01 with the E3D Hemera, with 3 perimeters, 3 top and 3 bottom layers at 0.25mm layer height and 20% cubic infill. I only tweaked nozzle and bed temperatures to suit each material, and the test model is the gear from my off-road platform that uses a 12mm hex to transfer torque. For the testing methodology, I printed 2 identical gears in each filament and crept up the torque in one until I experienced a failure, and then tried the second one at the same torque the previous one failed at to try to eliminate any issues with plastic deformation over time, which is something that all of these filaments do suffer from. Because I'm testing to destruction, the fixed gear needs to be super tough, so introducing a real Mod 2 spur gear. This thing wasn't that expensive, but it's huge and incredibly heavy. If it even gets marked at all during this testing, I'll be surprised. So let's kick things off with PLA filaments. PLA, or polylactic acid, is a polymer made from renewable resources such as cornstarch, and it's incredibly easy to 3D print with. These rolls of no-name PLA have been in my stash for years, and they printed perfectly. But what about their strength? Well, testing didn't start off too promising, with a torque wrench annihilating the yellow gear at its lowest torque setting of 6.8 Newton meters. So I ordered a smaller one specifically for this video with gradations of 2 to 22 Newton meters. Drop a like and make him feel welcome. 2 through to 4 were fine, but it was only at 6 Newton meters that I noticed the gear start to seriously deform, and then it failed totally at 8 Newton meters. pretty pathetic, honestly. Initially, I printed at 200 degrees Celsius, which I usually do for PLA, but was seen in the excellent experiments by Stefan over on CNC Kitchen that increasing the printing temperature can help with strength, so I bumped it up to 210, but that only increased the failure point slightly to 9 Newton meters. So it's not looking great for PLA, hey? Well, not so fast, because not all PLA is made the same, as you'll soon see. This grey is again just labelled PLA, I have no idea where it came from, but it very quickly surpassed the failure point of the yellow PLA. It did begin deforming visibly at around 15 Newton meters, and then... yeah, this is fairly old PLA, so perhaps it's become more brittle over time, but like, maybe you want that in a gear, because the strength difference was pretty incredible. But anyway, how do modified PLAs fare? These are PLA filaments with various other things added to modify their appearance, temperature resistance, and strength. And Polyalchemy should be quite a familiar brand on this channel, as I've used it countless times in projects in the past for its gorgeous shimmery look that it has. But is it stronger too? Well, yes, at least by a little bit. Gear 1 in the Polyalchemy Elixir PLA began deforming visibly at around 8 Newton meters, but then failed at 12 with just the teeth shearing. This was confirmed again with the second gear, so it turns out Polyalchemy isn't just good for looks, but can be pretty tough too, at least in this application. Polyalchemy Elixir PLA may be primarily for looks, but eSun's PLA Plus is an incredibly popular modified PLA with greatly improved toughness, at least according to the packaging. I reached out to Cubic Technology here in Australia, and they sent across a roll of eSun PLA Plus to test, along with a roll of eSun PLA ST, which is meant to be even tougher than PLA Plus, and a roll of this BASF Ultra Fuse Pro 1. I don't know if I meant to say BASF or BASF. Either way, I honestly didn't even know they made filament, but I'm glad Cubic Technology included it in the box because this stuff turned out to be quite the wild card. But anyway, let's start with PLA Plus from eSun. Predictably, it had no trouble withstanding the torque, which had annihilated the yellow generic PLA, and it wasn't up until around 13 Newton meters that deformation became quite noticeable before failing at 14 in a similar manner to Polyalchemy, where the gears sort of sheared over themselves. Gear 2 reflected the same result, which gives us a nice definable failure point. I had high hopes after that for eSun's newer PLA ST, especially considering the documentation promises to be super tough. But alas, I noticed quite severe deformation at only 9 Newton meters. This filament is definitely one of the softer PLAs I've tried, which is probably why it has such elongation at break compared to regular PLA. But with both gears failing totally at 11 Newton meters with teeth permanently deforming, it's pretty clear this isn't the best application for it. I think I'd be more inclined after this testing to use this filament for something like a motor mount or wheel hubs to take advantage of that much added toughness over the other PLAs I've tested. Finally, the Pro 1 PLA from BASF or BASF. While printing, I couldn't help notice it has a similar sheen to Polyalchemy PLA, but maybe a little duller, which is interesting. And as I worked my way up the torque levels, it became increasingly obvious that this material is something else. At 13 Newton meters of torque, which is way beyond the other PLAs failing catastrophically, it only deformed a little, then sprung back into shape. It wasn't until 15 Newton meters that some damage became evident, and 16 Newton meters that the teeth finally rolled over in a highly localized fashion. Gear number 2 exhibited identical strength, which is frankly insane for a PLA, and the fact that this print isn't even solid. But I might just have to find out in future just how much of a difference a solid print would make to that strength. Next up is ABS. No longer a popular choice for hobbyist 3D printing, but an important material to test due to its increased temperature resistance compared to PLA. I've had this chocolate colored generic cheap ABS for years, and with a heated bed, it prints quite clean, so I use it a lot for various prototyping applications. Something very characteristic of ABS is this tendency to go white when stressed, known as crazing. And this was very evident in the testing, starting at only 5 Newton meters. You can see it, and it starts spreading as the torque levels were gradually increased. Still, it wasn't until 13 Newton meters that the gear failed in a catastrophic manner, splitting across the teeth all the way down to the hub. Gear number 2 failed at a similar torque level and in a similar fashion, so not amazing, but not too bad either. To give ABS a fair shake, I also tested Compositum ABS, a premium ABS from Poland I've had since 2017, and I'm not sure the company even exists anymore. Still, I use it when reasonable durability and temperature resistance is needed for prototyping, but I fear I may have given it a bit too much credit over the poop-colored ABS, considering what it achieved was essentially the same. It failed at 13 Newton meters for both samples, which is the same as the other ABS, but still pretty decent. Next up, we have the copolyester's PETG and its lesser known brother, PCTG. Many people claim that PETG is the best option when it comes to durability and temperature resistance in a filament that's easily printable on budget hobby-level 3D printers. Which is sort of true in my opinion. PETG is easier to print without warping than ABS, but it does need to be dried to remove moisture and avoid excessive stringing. These gears were printed from Monocure clear PETG, and they are super clean. PETG is truly unrivaled in its transparency. But what about strength? I was a little apprehensive when testing these gears because PETG has a nasty habit of failing suddenly, and up until the breaking point, there was actually very little deformation until this happened. The crack was sudden and predictable for both gears at 10 Newton meters, and it extended right down to the hub. But what I find fascinating is how it ignores the layer lines, unlike the other filament samples I've tested. But let's say you don't want your copolyesters exploding into shards of plastic. Well, PCTG might be the ticket. I haven't used this material before, but Fibrology sent it over to try along with some other filaments, and it's pretty interesting stuff. I printed it with the same settings as PETG, but I did bump the bed temp to 100 degrees C as per the recommended settings. PCTG has a high impact strength compared to PETG, so I wasn't too worried about the sample exploding, but I had no idea what torque levels it could handle. The deformation was fairly minor, but certainly higher than PETG, but the gear withstood slightly more abuse before failing at 12 Newton meters by kind of tearing apart at the tooth, and the second sample failed in an identical manner. Okay, it's time to move on to a monster of a 3D printing filament that is PA, polyamide, or nylon. There are many kinds of nylon filaments on the market, but they're all incredibly strong. I've had this roll of Fibrology PA12 for some time, and it prints beautifully as long as it's fully dried. I'm talking 6 to 8 hours in a dehydrator at least, and you need to make sure the bed and ambient printing temperature is high enough to avoid warping. So, would you think nylon is the obvious choice for gears then, right? It's super tough. Well, let's find out. At all torque levels up to 10 Newton meters, the PA12 handled it like a champ. It deforms, yes, but then it springs back into shape, something that none of the other filaments tested so far do. But at only 11 Newton meters, it all goes horribly wrong. The gear didn't break, the teeth didn't deform, but the 12mm hex in the middle started to spin due to the softness of the material, and it just flexed. And that's the thing about nylon, it's incredibly springy, but not all that stiff, which makes transferring higher levels of torque quite challenging. After testing though, you wouldn't even know because both gears show absolutely no signs of damage at all. But what if there was a way to make it stiffer? Well, enter PA12 glass filled. Nylon being too soft for some applications is actually a well understood issue, and engineers have been combining it with fillers such as carbon or glass fibers in injection molding for ages, resulting in a more rigid product. And that's exactly what this filament aims to do. This is Fibrology's glass-filled nylon, and it's significantly more rigid than the virgin PA12, and shrinks less too, but it's also stupidly rough. It's one of the roughest filaments I've ever handled, and the prints reflect that. Even after drying, it's nowhere as clean as the nylon on its own. There's definitely quite a bit of definition lost along the profile of the gear teeth themselves. However, if they can still mesh, I can still measure. From the outset, the additional stiffness due to the glass fibers is evident with minimal tooth deviation, and this takes us well up past the maximum that nylon on its own, the PA12, could handle. You can notice the tooth deforming quite a bit, but springing back until we get to 15 Newton meters when it finally shears off. And with the second gear test, I verified this result, but in this case, the hub also spun, which reveals a weakness in my testing setup. If a gear this small is spinning a 12mm hex, then I would argue your drivetrain probably has bigger concerns. You could design a better mounting system like a large keyway, but for me, this tells me everything I need to know. So after all of that testing, here are the results in graph form, and there are some real surprises here. For example, PLA is all over the shop. We have the really poor performance of the yellow PLA to the unexpected good performance of the generic grey PLA to the incredible performance of the Bass Pro 1 PLA, which I just did not see coming. And then the nylons, which are very strong but are just a bit too pliable for a mechanical component like a gear, but I reckon they'd be fantastic for other structural components because they literally don't crack. They're just so incredibly tough. It's insane. But the whole purpose of this video was to find out which filament I wanted to use for gears for my off-road platform that is very nearly complete. And I think I'm going to use the Bass Pro 1 PLA. So the thing about PLA is the temperature resistance is going to be lower than something like a nylon. And I don't know how much of a difference that's going to make in this application. I don't expect these gears to get too hot, but if this platform was to start getting warm, then the gears would probably fail prematurely. And I might have to look more into like the PCTG, which again was this really surprising filament, maybe a little bit too soft for my liking, but again, a really strong contender. But this video also opened up so many more questions. For example, if you print a gear solid instead of with the infill, how much stronger will it become? And also, I really want to try some other filaments like polycarbonates. I didn't have any on hand to test in this batch, but I do have some on the way. For those who don't know, Sydney is now fully locked down with like another COVID wave, so we're kind of stuck, but I will order it in to do some future testing and then see how that goes. But yeah, in the comments, let me know what filament you would choose for your 3D printed gears and mechanical components, and what sort of failure mode do you think's most suitable? Like, do you want the gears to crack in half and fail suddenly, like we saw with the PETG, or do you want them to sort of deform and roll like with the nylon, or something else? Like, I'm not exactly sure how I would prefer the gears to fail. Ideally, I don't want them to fail at all, but personally, I think the rolling on the hub would be less damaging if a gear was to fail in the platform and then therefore protect my very fancy brushless gear motors. If you found this video interesting, maybe consider subscribing to Maker's Muse. My aim to empower your creativity through technology, and I'll force you again very shortly. Catch you later, guys. Bye.